to lecture 13 of this course on computational topology. So before I advance, do you have any quick questions with regards to what we have discussed so far, or anything with regards to the exam? If you have quick questions, please let me know. I'd be happy to take them now. All right. So I don't see any raised hand, so maybe we can advance. Okay, so if you remember, in the previous class, we discussed what is called as the Mayer-Vittoris theorem, right? So recall what is the purpose of this Mayer-Vittoris theorem. In some sense, if you have a complicated simplicial complex and let's say K1, K2 are subcomplexes of M, which are simple in some sense in that, we know they are, there is some way to compute their Betti numbers. So the Mayer-Vittoris theorem somehow relates the Betti numbers of this complicated simplicial complex in terms of the Betti numbers of this complex. Okay, so that's what loosely was the purpose of the Mayer-Vittoris theorem. So let's look at the formal statement of this Mayer-Vittoris theorem. So the statement goes as follows: let M be some simplicial complex and let K1 and K2 themselves be simplicial complexes such that K1 and K2 are subsets of M, right? So we require that both K1 and K2 be themselves simplicial complexes and also that they are subsets of M. So a common word for this property is subcomplexes, right? So M is a simplicial complex, K1, K2 are subcomplexes such that M is K1 union K2. Okay, so I emphasize again here that we do not require K1 and K2 to be disjoint. Okay, so as long as K1, K2 are simplicial complexes and their union is M, that is good enough. And then we let L denote the intersection of K1 and K2, right? And as we discussed in the previous class, whenever K1, K2 are simplicial complexes, their intersection trivially is also a simplicial complex. Then the Mayer-Vittoris theorem states that the following infinite sequence is exact, right? So this sequence sort of extends, forever in both directions. Okay, so I should also have an arrow in this direction, right? So it sort of extends in both these directions forever. And I have written the sequence in this fashion for only for convenience. In particular, you can see that what is here and what is here is basically the same, except that the n over here, okay, is replaced by n minus 1. Okay, so in that sense you can see that we start with hn of L, you look at the direct sum, then you go to hn of M, then you look at something similar to what you had over here, and from here you will go to hn minus 1 of M and the sequence will continue, right? So the Mayer-Vittoris theorem states that the following sequence is exact, right? And the other thing that I emphasized as part of the statement of the Mayer-Vittoris theorem was what are the vector space homomorphisms that are present over here. So there are some vector space homomorphisms here as well, right? However, defining them will take us away from the computational homology course. So that's why I will just say that there are some vector space homomorphisms over here which makes this entire sequence exact. However, it is important to know what these two vector space homomorphisms are, and I will soon tell you why it is important to know what these vector space homomorphisms are. Right? So what are these vector space homomorphisms? Well, these vector space homomorphism is made up of a tuple of two functions, right? So nu n is made up of in star and jn star, where in star and jn star are the homomorphisms induced by the inclusion maps I and j, where I is goes from L to K1 and j goes from L to K2, right? So I is takes an element in L, since L is a subset of K1, right? Since L is a subset of K1, every face in L will also be a face in K1, right? So I just maps sigma to sigma, right, for all sigma in L. And similarly, you can define J over here, right? So now let me emphasize why this vector space homomorphisms are important. They are important because, because of the following corollary. Okay, so the Mayer-Vittoris theorem directly says that there is some relation between these different homology spaces, whereas this corollary sort of explicitly says something about the Betti numbers of different dimensions. Right, so what it says is that if you look at the nth Betti number of this simplicial complex M, then this equals the nth Betti number of this simplicial complex K1 plus the nth Betti number of this simplicial complex K2 minus the nth Betti number of this simplicial complex L plus the dimension of kernel of nu 1 plus the dimension of kernel of nu n minus 1, right? So let's try to try and spend some time appreciating this relation. Okay, so the first thing you have to appreciate is that we have an equality, right? So we have an equality, meaning there is something on the left that we wish to desire to compute, right? And what we have is a formula that gives an exact expression for this quantity that we wish to compute. Okay, so that's the first thing. And the other thing is it somehow only concerns what happens about, I mean, so the terms on the right only concern k1, k2, L and so on, right? So these are things you should be able to compute, and what this relation tells us is that if you know these different things, you will be able to compute the nth Betti number of M as well. Okay, so this is a corollary that we sort of proved by using the fact that this sequence made up of 5 vector spaces is exact, right? So just by using this we managed to show this corollary, right? So this corollary is something we proved. The Mayer-Vittorius theorem is not something that we proved, right? So the Mayer-Vittorius theorem, I sort of said the proof is quite complicated and beyond the scope of this course. However, those who are interested, okay, they can look at the Mayer-Vittorius theorem in some of the algebraic topology textbooks. All right. So now thereafter what we did was, once we stated this corollary, we said, look, we can sort of interpret this theorem in a simpler fashion. In particular, we stated this proposition. Okay, so let's try to recall what this proposition was. So the proposition went something like this: let delta be a simplicial complex, right? And this is a simplicial complex on the vertex set V. Okay, so this is a simplicial complex on the vertex set V, and let sigma be a subset of V, right? So sigma is a collection of vertices in V, and sigma satisfies the property that the number of vertices in sigma is p plus 1 for some p bigger than equal to 0. Okay, now what is the property of sigma and how is sigma related to delta, right? So the property of sigma is that sigma itself doesn't belong to K. Sorry, I shouldn't say K, I should say delta over here. Okay, so recall that delta over here is a simplicial complex. So a simplicial complex is a collection of sets, right? And sigma over here is also a set, and we require that this sigma not be an element of delta. That is the first thing. Nevertheless, we require that this property hold, right? So let us try and understand what this property is. So the first thing that should bother you is that what is this delta p operator, right? So typically we define this delta p operator to go from Cp to Cp minus 1. So the first thing we have to ask is what is Cp and what is Cp minus 1? Well, these are, ideally I should write them as Cp of delta to Cp minus 1 of delta, right? Which means that this is the collection of all p chains in delta, and this is the collection of all p minus 1 chains in delta, right? So this Daba P operator takes this Cp of delta to Cp, I mean, takes an element in Cp of delta to Cp minus 1 of delta. So the first thing that should bother you is, oh, sigma does not belong to delta, right? Sigma does not belong to delta. So in particular, sigma does not belong to Cp of delta, right? So I hope you are able to see the difference between this statement and this statement. When I write this statement, I am interpreting sigma as a set. So this set does not belong to the collection of sets in delta, right? And when I write something like this, I'm interpreting sigma as a p chain, right? So I can interpret sigma as a p chain, and I'm claiming that this p chain is not part of Cp of delta, and the reason is that sigma does not belong to delta, right? So the first question that must arise in your mind is, how then can we define this Daba P of sigma? Well, that is a valid question. Since sigma does not belong to Cp of delta, one directly cannot talk of Daba P of sigma. Nevertheless, what we will imagine Daba P of sigma to be. So let's say sigma is made up of V0 to Vp, right? So I will imagine Daba P of sigma to be, although I cannot apply Daba P of sigma because sigma does not belong to Cp of delta. Nevertheless, I will artificially define this Daba P of sigma to be summation P0, I mean in the usual way, so I'm not doing anything. So this is how I will define. Okay, so this goes from this to this, right? So I can nevertheless define dabba P of sigma directly in this fashion, right? And one then is interested in making sure that this output lies in Cp minus 1 of delta, right? So even though sigma does not lie in delta, we require that after you apply dabba P on sigma, this lies in Cp minus 1 of delta, right? So this condition is equivalent to the condition that all the boundary faces of sigma are in delta. Okay, so now let me try and explain this using some figure, right? So let's say you had this simplicial complex 1, 2, and 3, and let's say sigma was the face. Okay, 1, 2, 3, right? So it is this face over here, but this original simplicial complex, which we denote as delta, does not have sigma, right? So clearly sigma does not belong to delta. However, if you apply dabba 2 on delta, I hope you agree that we would end up with 1, 2 plus 1, 3 plus 2, 3. Now this thing over here, okay, I hope you agree, belongs to C1 of delta, because C1 of delta, in particular delta, has these three edges, right? So C1 of delta will also include the sum of the formal sum of these edges, which is exactly this, right? So in this sense, you can see that although sigma does not belong to delta, okay, the output of dabba 2 on delta, this lies in C1 of delta, right? So for this proposition, it is important that such a claim hold true. So I will pause here. Such a condition hold true. So I'll pause here. If you have any questions on understanding this condition, please let me know. Yes, Amritandu, go ahead.
Sir, sigma has to be a simplex, or can it be a simplicial complex also?
So sigma is a subset. So your question is, can sigma be a simplicial complex? Is that your question?
Yes.
So notice I have said that sigma is a subset of V. It is one subset of V. It's not a collection of subsets of V.
Okay.
Is this okay? I hope that answers your question.
Okay.
Okay. Yes, Deep, go ahead.
What are we trying to capture here with this condition, this del P sigma belonging to Cp minus 1 delta?
So we want to state some result later, okay? And for this result to hold later, we require that such a condition hold. Is that okay? So I mean, this is exactly what we require. So what we are trying to do is we are trying to take a simplicial complex and we are trying to add a face to it, right? Now, what we want to ensure is that, see, when so let's say if so let me sort of maybe give a simpler example, right? So let's say there is this edge 1, 2, sorry, there is a simplicial complex where there are these vertices 1, 2, and let's say I want to add this, or maybe I'll draw it this way, and let's say I want to add the edge 1, 3 over here, right? So I want to add the edge 1, 3. So in particular, notice that the vertex 3 does not belong to this simplicial complex. Do you see that, Deep?
Yeah.
So how do I add this over here? So the first thing you'll have to do is you'll have to add this vertex 3 and then add this edge. Do you agree?
Yeah.
Right. So what I'm saying is that, I don't want to ever be in such a situation. Whenever I want to add such a face to a simplicial complex, all its boundary faces must already be present in the previous setup. Is that okay? That's all I'm requiring.
Okay.
Okay. Jacob, can you answer? Please ask your question.
Then how can we add vertex 3?
How can what?
If you want to add a new vertex,
so then what I'm saying is that you first add this vertex 3, okay, and then you add this edge 1, 3. So I don't want to, look at adding this edge 1, 3 in one go. I want to first add vertex 3, then you say this result applies. Then once you have the vertex 3 in the simplicial complex, I can add this edge 1, 3. Then this result applies. Is that okay?
So dabba 0 of 3 must be something, right?
So dabba 0 of 3, Okay, so this is, so we will work in the usual homology setup. So let me emphasize that. So we will work in the usual homology setup, right? So so if you take DABA 0 of 3, this is going to be 0, right? So trivially, this in the case that sigma is like, let's say, one vertex, and this vertex was not there in delta, right? So this is trivially going to belong to CP minus 1 of delta, which is in this case going to be minus 1. Is this okay?
Yeah, yes, yes.
So what I'm saying is that you can add a vertex, but you cannot add an edge before adding the vertex. So that's the kind of situation that this proposition is trying to look at. Okay, where you sort of don't do a complicated operation. Is that okay? Do you have any more questions? Please let me know.
Yes, okay.
All right, thank you. So let's advance. Okay, so this is the situation. Okay, so the proposition says that we have a simplicial complex. We want to add sigma to this simplicial complex. However, sigma must be such that this sigma does not belong to delta, so that the addition makes sense. If sigma was already in delta, the addition wouldn't make a lot of sense, right? It's like you take a simplicial complex, a face is already there in it, so how can you add that thing? Nothing will change, right? So we want to look at the case where sigma does not belong to delta. However, we don't want to be in a situation where the subfaces of sigma are not there in delta already. Okay, so that will be a complicated situation with regards to this proposition. So what we require is that all the boundary faces of sigma are already there in delta. Okay, so that is the scenario that we are interested in as part of this proposition. Is this okay? So these two conditions together, okay, is equivalent to saying that sigma does not belong to delta. However, all the boundary faces of sigma are in delta. All right, so far so good. Then what does this theorem say? Okay, so first of all, notice that we are looking at a very specific case where the cardinality of sigma is p plus 1. In particular, we are trying to add a p-dimensional face, right? So this result says that for every j, okay, so there is a typo here, for every j which is not in p minus 1 comma p. So for every j which is not in this collection p minus 1 or p, right? So you are adding a p face. So what you are saying is that every other Betti number, okay, except for p minus 1 to p, those Betti numbers are preserved. Okay, so that is the first thing. So when you add a phase delta, sigma to delta, then every Betti number except these guys are preserved. Okay, so this I will refer to as the preservation property. Okay, so now let's move on to the second part of this statement. So this statement says that if this daba p of sigma lies in image of daba p. Okay, so this statement needs to be interpreted appropriately, but we will come to it soon. So if this statement holds, then what happens is that if you add sigma to delta, then the pth Betti number will increase by 1 and the p minus 1th Betti number will remain unchanged. So I will refer to this condition as creation. So why do I say creation? Because you can see that one p dimensional or p plus 1 dimensional hole is being created over here. That's why the pth Betti number increases by 1, right? So what this statement is saying is that when you add sigma to delta, you are creating a p plus 1 dimensional hole if this condition is true. Okay, so if this condition is true. On the other hand, if this condition does not hold true, then you are not going to create a p plus 1 dimensional hole. Instead, you are going to destroy a p dimensional hole. That's why if you notice, the p minus 1th Betti number decreases by 1 and the pth Betti number remains the same. Is this okay? So this is this proposition in some sense is saying when you add sigma to delta, what could happen? So the result is states that all other Betti numbers except the p minus 1th and pth Betti number will remain unchanged. If this condition is true, then a p plus 1 dimensional hole is created. And if this condition is true, which is the opposite of this, right, a p dimensional hole is destroyed, right? So in this sense, this proposition says that some Betti numbers are preserved. It is possible that when you add sigma to delta, some some new hole is created, or it is also possible that when you add a phase to delta, right, some old hole got destroyed, right? So this is the best way to remember this proposition, that this proposition talks about preservation, creation, and destruction, which in some sense are the three aspects of life, right? Preservation, creation, and destruction. All right. Okay, so now before I sort of state this condition and explain it, let's look at an example, and then you will be able to appreciate what this theorem is trying to say. Okay, so let's look at an example, and in particular we want to look at the case where P is 1. Okay, so which means that this is the simplicial complex that is there currently. So you can see that it has 5 vertices and 3 edges. Okay, and I want to add one edge to this simplicial complex. Okay, so I hope you agree that when I try to add an edge, there are two kinds of edges. Okay, first edge is of this kind, right? The edge whose two endpoints lie in the same component, right? So I hope you agree that this graph has two components. The first is this and the second is this. So if I try to add an edge, you could either add an edge whose two endpoints lie in the same component, or you could add an edge whose two endpoints lie in different components. Do you agree? Let me repeat. When you try to add an edge to this, either you could choose this edge, or maybe this edge, or maybe this edge, right? So if you notice the characteristics of these edges, they have the following different natures. First is the case where all the both the endpoints lie in the same component, and the other is when the endpoints lie in different components. Is this okay? So either this, or this. Now let's see what happens when I try to add a component whose endpoints lie in the same component, right? So can one of you volunteer and tell me, when I added this blue edge to this simplicial complex, what happened? Can one of you volunteer and tell me what happened? Yes, Deep, please go ahead.
Yeah, beta 1 will increase by 1. It's 0 currently, but it will increase.
Yeah, beta 1 increased by 1. So I hope you agree that so original beta 1 was 0 and the new beta 1 is 1, right? So maybe I'll say old, new. So old was 0, now it has increased by 1. And what about Betti 0? Did Betti 0 change? Did Betti 0 change?
I'm not sure. I think.
See, Betti 0 counts the number of components. Is that okay? We are looking at the usual homology setup, right? And in the reduced homology setup, Betti 0 counts 1 less than the number of components, right? So originally, in the beta 0 case, old situation is, since there were 2 components, it will be 2, and the new situation is 2. Do you agree? Right?
Yeah.
So I hope this is clear. When I added the blue edge, I created a two-dimensional cycle. Now let's remove that situation and let's see what would happen if I add, let's say, this green edge. Now can one of you tell me what happened? Can one of you please volunteer and tell me? Yes, Rankit, go ahead.
Beta 1 will remain the same.
Very good.
And beta 2 would, beta 0 would decrease to 1.
Very good. So beta 1 was 0 initially, now it is 0 initially. Now also it is 0 after the addition of the edge, whereas beta 0 to begin with it was 2. After the addition of edge, it reduced to 1. So you can see that when I added this green edge, right? When I added this green edge, okay, there was destruction. Is this okay? There was some destruction. So when I added this blue edge, there was creation, whereas when I added this green edge, there was destruction. And this is exactly what this proposition above is trying to capture. When you try to add a p-dimensional face, either you could create a p plus 1 dimensional hole, or you could destroy a p-dimensional hole. That's what this theorem is, or this proposition is trying to tell us, right? And it is also telling us what is the condition under which this should occur. So now, we will sort of keep this example in mind, and we will now try to interpret, why does this thing, why should this occur? Like, what is this condition trying to tell us, and why should this imply this should happen, and why should this imply this should happen? Is this okay? So that is what we are going to interpret now. So first, let's see what is this trying to say. Okay, so I mean, this is sort of a loaded condition. So let's go over it carefully, right? So maybe I'll write it over here. So this is dabba p of sigma belongs to image of dabba p, right? So ideally I should have written it in this fashion, that dabba p of sigma belongs to image of dabba p of delta. Okay, so let's try to understand what is over here, right? So you have delta, right? So this is already a simplicial complex. So you can talk about Cp of delta, right? And you can talk about dabba p. So dabba p will go from Cp of delta, right? Dabba p will go from Cp of delta to Cp minus 1 of delta, right? So now you can, so this is a vector space homomorphism. So you can talk about the image of dabba p of delta, right? So when I mean, when I write something like this, I mean the image of this operator over here, right? So this is, the image of this operator over here. So this will be a subset of Cp minus 1 of delta, right? So what we are interested in knowing, I mean, this condition is equivalent to asking whether this, right, lies in image of dabba p of delta, right? So let's first try to interpret it over here, right? So let's see what happened when this blue edge we tried to add, right? So this blue edge, right? So let's call this as E. So dabba 1 of E. Okay, so let's label some vertices. So let's say this is 1, 2, and 3. So I hope you agree that dabba 1 of E is 1 plus 3. Is this okay? Now let's look at what is image of dabba 1 of delta, right? So let's try to interpret this. So in the image of dabba 1 of delta, we don't have to worry about this edge, right? Because delta doesn't have this edge. So what is image of dabba 1 of delta? So let me label this as 4, 5. Right? So I have to basically ask, if I take every possible one chain in delta, right, what would be the output when I apply dabba 1, right? So of course, if I take the zero, the one chain with zero support, we will get this. Then I will get 1 plus 2, I will get 2 plus 3, I will get 1 plus 3, and I will get 4 plus 5. Is this okay? So these are, this is what is the image of dabba 1 of delta. So let me pause over here. If you have any questions with regards to how I got this image of dabba 1 of delta, please let me know. And I'll also maybe wait for a second or two for you to stare at this set and, make sure you understand why we obtained this. Is this okay? All right. So I don't see any raised hand. So maybe we can advance, right? So yes, Jacob, please go ahead.
Okay, 1 plus 3 came through 1, 2 plus 2, 3, right?
That's correct. Yes. Yes.
Okay, okay.
Okay. Right. So yes, you are indeed right. Okay. So you can see that in this scenario, E does not belong to delta, right? So E does not belong to delta. However, dabba 1 of E, which is 1 plus 3, this belongs to image of dabba 1 of delta. So you can see this over here, right? And this 1 plus 3 comes because of the chain 1, 2 plus 2, 3, right? So this one chain is already present in C1 of delta. So if I apply dabba 1 of this, I hope you agree that we will end up with 1 plus 3. So in that sense, you can see that dabba 1 of E indeed belongs to this, right? So since this belongs to this, as per the above proposition, when I add this edge over here, it should lead to creation, okay, and it should lead to creation of a two-dimensional hole. Is this okay? Now let's look at a different scenario. So let's look at the scenario where we try to add some edge like this. Okay, so in this case, let's call this as E. So in this case, your edge E is 3, 4, and dabba 1 of E is 3 plus 4. Is this okay? Dabba 1 of E is 3 plus 4, right? So since this is 3 plus 4, I hope you agree that this does not belong to image of dabba 1 of delta. Okay, so this does not belong to image of dabba 1 of delta. So which means that this condition holds true. So when I add this green edge, I am going to lead to destruction, right? I'm going to use my destruction avatar, and this means that since P is 1, the zeroth Betti number should reduce by 1 when I add this edge E to this simplicial complex. Is this okay? And what this proposition is saying is that what we observed in the graph case, okay, is not just restricted to the graph scenario, it actually holds true in the higher dimensional faces as well, right? So as an example, let's say you started off with this skeleton, right? So let me try and tell you what we have. We have these four vertices, right? So we have these four vertices, and since we have these four vertices and we have these six edges, right? So together they form a simplicial complex. So this is our delta, right? So now what I'm going to do is I'm going to, let's say I try to add this triangle to this simplicial complex, right? So if I try to add, let's say sigma is 1, 2, 3, right? So then if I take daba 2 of sigma, I hope you agree that we will end up with 1, 2 plus 1, 3 plus 2, 3, right? Whereas image of daba 2 of delta, right? So this is going to be this trivial thing because delta by itself doesn't have any triangle, right? So you can see that this does not lie over here, and consequently when I add this triangle, when I add this triangle to this simplicial complex, what will happen is that my first Betti number, okay, will reduce by 1. Is this okay? When I add this triangle, my first Betti number will reduce by 1. So can one of you tell me what do you think must be the Betti number of this simplicial complex? What do you think? How many holes do you see here? So if I gave you this simplicial complex with 4 vertices and 6 edges, what do you think is Betti 1 should be? So there is one hole here, there is one hole here, there is one hole here, and maybe there is one hole here as well, right? So what do you think your answer should be?
4.
Can one of you
4.
volunteer? Please raise your hand. I don't know who
4.
is speaking. Yeah, Deep, go ahead.
Yeah, 4. 4
4.
faces. Yeah.
So your guess is that Betti 1 over here is 4. Rankit, do you agree or disagree?
Yes, sir. 4.
4. Okay. So is there anyone who disagrees, maybe has a different answer? Is there anyone who has a different answer? Okay, so I'll say that I have a different answer, right? And my claim is that for this, setup, Betti 1 is actually 3. So can one of you, argue that Betti 1 here would actually be 3 and not 4? Indeed, it appears that there are these 4 holes, right, which correspond to each of these triangles that you have, right, which corresponds to each of these 4 triangles. So it appears there are 4 holes, but my claim is that Betti 1 is 3. Can one of you quickly argue out why Betti 1 should be 3? Okay, so what I'll do is I'll allow you to think about it after the class, right? And maybe you can try and figure out why Betti 1 should be 3. Yes, Agnit, you had a quick answer. Agnit, please unmute.
If you look at this pyramid, then if we sum up the triangles that of 1, 2, 3, 1, 2, 4, and 1, 3, 4, then we will get 2, 3, 4.
Precisely, but you have to be a bit more careful. You cannot, I'm not sure if you said 1, 2, 3 plus 1, 2, 4 plus.
I meant the edges of the triangle because.
Very good. Okay, so you have to somehow, so recall that this cycle is a whole. This cycle, sorry, I shouldn't say this. One chain is a cycle, lies in the kernel, right? So this one chain also lies in the kernel of daba 1. This one chain also lies in the kernel, and this one chain also lies in the kernel. However, Betti 1 is the dimension of this vector space, right? It's not counting the number of elements, and you can see that, as Agnit mentioned, this one chain one can express as this one chain plus this one chain plus this one chain, right? So because of this reason, all these 4 one chains are not independent, right? So there are only 3 independent one chains, right? And that's why Betti 1 over here is 3. Okay, so now when I add this particular triangle, right, when I add this particular triangle to delta, you will be able to see that Betti 1 actually reduces by 1, and this resulting simplicial complex Okay, this resulting simplicial complex will have Betti 1 now equals 2. Is this okay? So you can do this exercise more carefully, and more importantly, what this proposition tells us is that, you know, whenever you add one phase, okay, how does the Betti number change? Okay, so let me pause here for a second or two. If you have any questions in understanding this proposition, this may be a good time to ask, because once you understand this proposition, the incremental algorithm by Delfinado and Edelsbrunner should now become a piece of, should become a cakewalk now. So if there is anything that you didn't understand in this proposition, please let me know. All right, so I don't see any raised hands, so let's advance. So as I said, okay, now we can discuss an incremental algorithm to compute the Betti numbers of a given simplicial complex. Okay, so let's first try and understand what this algorithm is. So what is the input to this algorithm? Well, the input to this algorithm is some simplicial complex. Okay, so you take a simplicial complex and you want to give this as input to this algorithm, right? And what is the output that we expect? The output that we expect is Betti P of delta for all P in the set of set of integers, right? So I want to compute every possible Betti number of delta, right? So before I run this algorithm, I have to do some initialization. Okay, so everything that I do is in some sense to be in a position where I can apply this proposition from above. Okay, so that's the reason that I'm doing this initialization step. So the initialization step goes as follows. So let's say delta had m faces. Okay, so it had m many faces, and what I do is I order these m faces such that, let's say the first phase we will now call as sigma 1, the next phase I'll call as sigma 2, and so on, and the mth phase is sigma m, right? I would like to emphasize that these faces could have different dimensions, right? These faces could have different dimensions. So all the faces in delta, I have ordered them, and I am ordered them, meaning I'm saying this is the first simplicial, this is the first phase, this is the second phase, this is the third phase. So I have given some ordering. And how do I order? So the ordering should satisfy the following condition, that if you look at the first I faces, right? So you look at sigma 1, sigma 2, sigma I hope you agree that this is a collection of faces. So for every I, this delta I, right? So delta I is the collection of all the faces from sigma 1 to sigma m, right? So delta I is the collection of faces from sigma 1 to sigma I. So this collection must be a simplicial complex for all I. Is this okay? So let me pause here. If you have a question on understanding this statement, let me know. Okay, so this is how I order the faces, and I would like to emphasize that there is no unique ordering. Okay, there are several ways you can order the faces such that this condition actually holds true. If you have any question, please ask, otherwise we can advance. Yes, Pankaj.
Do you have any example for this? I didn't understand this.
So let's say this is your simplicial complex. Okay, let's say 1, 2, 3. So can you tell me what are the different faces in delta, Pankaj?
It's 1, 2, 3.
Yes.
Then 1, 2, 1, 3,
and 2, 3. Is
and
this
2,
okay?
3.
These are the different faces. Now let's give them some names. Okay, so what I want is okay, so instead of giving names and then ordering, what I'll do is I want to order these faces, right? So you could have ordered them in the following way, right? So let's say 1, 2, 1, 3, 1, 2, 3, and 2, 3, right? So I'm saying that this way of ordering is not good. Why is it not good? Because if you just look at 1, 2, so right, delta 1 will be made up of 1, 2. Is this a simplicial complex, Pankaj?
No.
No. So this way of ordering is incorrect. On the other hand, if you sort of said, let's say 1, 2, 1, 2, 3, 1, 3, 2, 3. Do you think this is a good ordering, Pankaj?
I think yes.
Right, so it is, right? Because if you look at delta 1, this will only be made up of 1. If you look at delta 2, it will be made up of 1 comma 2. Delta 3 will be made up of 1 2 1 2. So I hope you agree that delta 1, delta 2, delta 3 all are simplicial complexes. Do you agree? Right, now
Yes.
delta 4, I'm adding 1 2 1 2 3. Is this a simplicial complex?
Yes.
Right, so you can see that this way of ordering is good enough. But you could have also ordered these faces as 1 2 3 1 2 1 3 2 3, right? So you can see that there is no unique ordering. Does that help?
Yes, a lot. Thank you.
Okay. All right. Okay, so this is the way you are supposed to order, so that if you look at delta I, which is the collection of these I faces, I many faces, right? This each intermediate thing that you have should also be a simplicial complex, right? And to begin with, what we will say is that delta 0 must be the empty simplicial complex, right? So it doesn't have any face. So our idea, so when I say incremental, what does it mean? Okay, so that is what I'm going to now explain. What does incremental mean? So one way is you could have taken this simplicial complex, right, and you could have sat down trying to compute all Betti numbers at one go, right? On the other hand, this incremental means that you start off with the empty simplicial complex. So I hope you agree that for the empty simplicial complex, beta j will be 0 for all j in the set of integers, right? Because this simplicial complex has nothing, right? So one would expect that all the Betti numbers are 0. And now what I'll do is, to this empty simplicial complex, I will add one face at a time, right? So I'll first add sigma 1, then I'll add sigma 2, then I'll add sigma 3, and I will sort of incrementally build this simplicial complex so that this delta 0 becomes delta 1, right? And it becomes delta 2 and so on, delta 2, delta 3. By at each time I'm adding one face, right? So by adding this one face at a time, I hope you agree that at the end I would have added all the m faces. At that time I would reach delta m, and this would be delta, right? And the incremental algorithm, or the idea is that in each iteration where we are just adding one face, we are interested in knowing how the Betti number changes, right? How the Betti number changes from here to here, how the Betti number changes from here to here, how the Betti number changes from here to here, and eventually we would be able to compute the Betti number of delta m, right? Each time only one Betti number will change, right? And why do I say only one Betti number will change is because of this proposition. You can see that when I add a face, only this Betti number changes or this Betti number changes. All the other Betti numbers remain the same. If this condition is satisfied, the pth Betti number changes. If this condition is satisfied, the p minus 1th Betti number changes. So you can see that when I add a face, only one Betti number will change. All the other Betti numbers will remain the same. So incrementally, I'm going to add these faces one by one, and incrementally, I'm going to update my Betti numbers as I keep adding my faces. Okay, and that's why this is referred to as the incremental algorithm. And the algorithm is very, very straightforward, and it goes as follows. Okay, so let me zoom out so that you can see the whole algorithm, right? So I have a for loop which goes from I equals 1 to m. So recall that these are the number of faces that I have in delta, right? So what is the first thing I do? As soon as someone gives me, so I'm talking about the ith step in this for loop. So the in the ith step, I would be given this sigma I, right? So I would be given this sigma I. So what I have is, at the beginning of this ith step, I would have delta I minus 1. I would know the Betti numbers of this delta I minus 1, right? And now I'm going to add to this sigma I, and my question, and this will be delta I. So at the beginning, I know the Betti numbers of delta I minus 1. At the end of this iteration, I would know the Betti numbers of delta I. That's the process. Okay, so I know sigma, I mean, I'm given sigma I at the beginning of this, iteration, ith iteration. So the first thing I do is I first note down the dimension of sigma I. This is the number of vertices in this minus 1. So this will be this. So if p is 0, okay, if p is 0, then what I do is I simply update my 0th Betti number, right? So basically, if I add a vertex, I'm going to simply update my Betti's number. So if whatever was my original Betti number, the new Betti number is going to be 1 plus the old Betti number. Is this okay? It is going to be 1 plus the old Betti number, right? On the other hand, if P is not 0, that is I'm trying to add a higher dimensional phase, then I check this condition. If this condition holds, then I know that I am going to create a cycle, right? I am going to create a cycle, and in that way I hope you agree that Betti P will increase by 1. On the other hand, if these two conditions are not true, which means that this the opposite of this condition holds, then the P minus 1th Betti number should decrease by 1, and this is how this entire algorithm proceeds. So at each step I basically have to check whether some condition holds or not, and depending on that I decide whether to increase my Betti P or decrease my P minus 1th Betti number. So maybe I'll pause here. Let me know if there are any questions with regards to this incremental algorithm. Okay, so this algorithm was proposed by Delfinado and Adelsbrunner. Okay, and I don't remember, every time I sort of say this, I say I don't remember. I think that's not good, but I think it is in the year 92 or 93. So you can see that this algorithm is almost 30 years old, right? This is, in some sense, a basic algorithm to tell you how to compute the Betti numbers in an incremental fashion. So let me pause here. If you have any questions with regards to this update rule, please let me know. We will do an example on the next page, and that will tell you, how does this algorithm proceed. So, if you want to wait until the example, that's also fine. But if there are any technical questions with regards to the update rule of this algorithm, please let me know. Are there any questions? Yes, Rankit, please go ahead.
So is this the most optimal algorithm possible, or better algorithm exists?
So, so you have to first ask optimal in what sense? Optimal, is it in the space complexity sense, or is it in the time complexity sense, and so on and so forth, right? So, this is an incremental algorithm, right? So I have not told you whether this is efficient or not, and also I have not told you how to do these checks. Is that okay? So first of all, I have not told you how does one verify whether such a thing holds or not, right? So this should be a question that should have arisen in maybe someone's mind, because this is in some sense looks to be an algebraic condition, right? So like this is some phase daba p is some operator. I am applying it on sigma I, and this image of daba p is some set. I'm trying to see if this lies over here or not, right? So the first thing is, how do I verify whether this condition holds? And if you think about it, this is the hardest part in this update rule. Do you agree, Rankit?
Yes, sir, exactly.
Right, all these things are non-trivial, right? Doing some addition or increment, I hope you agree that these are not the the most time consuming parts in this algorithm, in this update rule, right? The only thing that is going to be time consuming is verifying this condition. Do you agree? Right, so to answer your question whether this is the most optimal way or not, we have to ask, how does one solve this, verify this condition? Do you agree?
Yes, sir, absolutely.
All right, so let's try to discuss if how to verify this condition. Can one of you maybe propose how do you think one could go about doing this? Okay, and the hint is that everything over here is related to linear algebra, so we have to do something in that sense. So yes, Jacob, please go ahead.
You can use the matrix representation.
Very good. So matrix representation. So let's say you have some. So let me first write it. Our goal is to check whether daba p of sigma lies in image of daba p of delta I minus 1. Okay. So this is the condition that we have to check. So at the ith step, I know delta I minus 1, and I'm going to add sigma I to it to make it delta I. And this is what I need to check. So as Jacob pointed out, okay, this daba p will go from Cp of delta I minus 1 to Cp minus 1 of delta I minus 1. So this is a vector space, this is a vector space, this is a vector space, this is a vector space homomorphism. So this is a linear map, and I can talk about the matrix representation for this. Right, so I can talk about the matrix representation. Very good. So far, so good. Maybe I'll emphasize that this is a DABA P of delta I minus 1. Right, so this is what I have. Maybe I'll write it properly. So this is I minus 1, and this is the matrix representation. Okay, so maybe I'll say matrix representation. Okay, and so that this is easy, let's call this A. Okay, so there is some matrix A. Very good. So Jacob, what is the next step? How do I check whether this lies in the image?
It's the column space of this matrix.
Very good. So you are interested in knowing whether this lies in the column space of A. So how do I write it down? Like, what is the formal mathematical way of writing this? Whether something lies in the column space, right? So this is a
combination of columns.
Yeah, that is true. Maybe I'll maybe help you a bit. See this delta DABA P of sigma I. I hope you agree that because of this the way we are constructing, and at each step we are ensuring that delta I minus 1 is a simplicial complex, right? So because of this thing, it will always be the case that sigma DABA P of sigma I belongs to this. Okay, so even though sigma I does not belong to delta I minus 1, it will always be the case that the boundary of sigma I, okay, this will always be in P minus 1. So what this means is that, I can find the vector representation. Okay, so I can find the vector representation of DABA P of sigma I in the basis of Cp minus 1 of delta I minus 1. So let's say this vector representation is B, right? So you have this matrix A, you have this vector B, and the question is whether B lies in the image, or in the language that Jacob used, does it lie in the column space of A? So how, is there some mathematical way of writing this question? B lies in the column space of A. What is the mathematical way of writing this question? Is there some linear combination of the columns of A which equals B, right? So I hope you agree that this thing is equivalent to figuring out if AX equals B has a solution. Okay, so the end of the day, the story is that if you want to check this condition, right? If you want to check this condition, what you do is you take the vector representation of this. Let's call this as B. You take the matrix representation of DABA P of delta I minus 1. If you call it as A, our goal is to solve this system of equations, right? And basically we are trying to know if trying to figure out if B lies in the column space of A, which is equivalent to asking, is there some linear combination of the columns such that this linear combination equals B? So let me pause here. Let me know if you if you are able to relate this to this condition over here. Do you have any questions? Please ask. Yes, Deep, please go ahead.
Yeah, I have a question regarding the matrix representation. So, like, if this delta is too big, I think I had asked this before, but again I'm a bit confused. So, if it is big, then again I need to compute this basis vector, so to speak, so that I can form this matrix, right? In some sense. So I want to solve this system of equations. So how do I do that? For small cases, I can do it by hand.
Yeah, you will have to use computers to solve this, but nevertheless you are thinking whether if my A will have like several rows and several columns, solving this is going to be hard. Is that your question?
No, I mean that I still have programs to do that, but I need to form that A, right? The matrix A, for which I need the basis representation for Cp minus 1 delta for each P. So that itself will be.
I'm not sure if you need the. I'm not sure if I understand your question. So recall how we constructed this A over here, right? So maybe I'll just show you a simple example. Let's say this is my delta, right? So it has 3 vertices and 3 edges. Do you agree? Right? Yeah. So if I ask you what is the matrix representation for this, what you will do is you will first, so let's see, this will be DABA 1 has to go from C1 to C0, right? So I have to first write all the three vertices here, and then I will write the three edges here, and I'll just put 1 1 sorry 1 0 sorry 1 1 0, and this will be 1 0 1, and this will be 0 1 1. This is how I construct this matrix. Are you worried that I may not be able to construct the matrix?
Yeah, I mean, I'm just thinking if it's a really big, complicated, simplicial complex, I still do the same thing or something else.
I mean, so I am not, see, the part of this course is not to tell you how to efficiently do it. Is that okay? That is, so your question is more suitable for maybe a computational linear algebra course. Is this okay? Right?
Okay.
Because your questions are how do I do it efficiently? That is not the question that we are asking in this course. What we are asking is how to do it, right? So I'm saying you have to solve this equation, but I'm not telling you how to efficiently solve this equation. That's an interesting question on its own right. Do you agree?
Okay. Yeah.
Right. So I'm not telling you that, and I mean, to be honest, I do not have expertise in that answer as well. But what I'm saying is that, look, at the end of the day, you have to solve this linear system of equations. If there is an efficient way to solve it, you can use this and make verification of this condition efficient in that sense. Does that answer your question, Deep?
Okay.
Right?
Yeah.
At the end of the day, all I'm saying is that this algorithm, the most complicated step is this verification, and how complicated it is. Instead of telling you the answer, I'm saying that, look, here is another problem, and this problem is equivalent to that problem. And what is that problem? This problem is equivalent to solving this system of equations. Is this okay? Right?
Yeah.
That's all I'm saying. I'm not saying anything more than this. Do you agree?
Okay. Yeah. Okay.
Okay, so now how you solve this efficiently and all those things, if you are interested, you can look up the literature on this, and then see, okay, I have this A, I have this B, I want to find X, and I want to in particular check whether this system of equations has a solution or not. If it has a solution, this condition holds. If it doesn't have a solution, then this condition fails to hold, and then you will be in the else part. So at the end of the day, the time consuming part or the time consuming step is this verification, which is as hard as solving a linear system of equations. So what is the whatever are the limits in solving this linear system of equations, all those limits will hold with regards to verifying this condition over here. All right. Okay. So with this, let's try to solve a simple example. Right. So what I want to do is, let's say this is the simplicial complex, and I want to compute the Betti numbers of this simplicial complex. Is this okay? That's my goal. And the way I'm going to do it is, I'm going to make use of this incremental algorithm to compute the Betti numbers of this simplicial complex. Okay, so for simplicity, I have ordered the faces as follows. I start with vertex 1, I start with vertex, I mean, the next is vertex 2, the next is 3, then I have the edge 1, 2, 2, 3, and 1, 3. But as I mentioned before, this is not a unique ordering. I could have as well set sigma 3 to be, 1, 2, sigma 3 to be 1, 2, and sigma 4 to be 3. That would have also ensured that this ordering is valid from the perspective of the the incremental algorithm. All right. Okay. So I hope the goal is clear. This is the simplicial complex. I want to find the Betti numbers of this simplicial complex. That's what I'm trying to do now. However, of course, I could have directly, sat down to compute the Betti numbers of this simplicial complex. But instead of directly trying to find it, what I'm going to do is I'm going to incrementally update the Betti numbers of this simplicial complex. So what do I do is, as first step, I set delta 0 to be the empty set and set all Betti numbers to be 0, since the Betti numbers of the empty simplicial complex are indeed 0. Is this okay? So because of this reason, I set all Betti numbers to be 0. Right. So now what I do is, I'm going to take this first vertex and add it to this simplicial complex. Okay, so that is what I'm going to do. I'm going to take this and going to add this. Right. So delta 0 is empty. Sigma 1 is the set with vertex 1, and delta 1 is, I'm going to take delta 0 and to that I want to add sigma 1, and that will create delta 1 for me. So my goal right now is compute the Betti numbers of delta 1, using the fact that this and this, together form delta 1. Okay, so that is what I want to do, right? So what does this proposition tell us? The proposition tells us that, since this sigma 1, okay, has dimension 0, right? The only thing that could change is Betti 0 or Betti minus 1. All the other Betti numbers are going to remain the same, right? And now we have to check whether it will increase Betti 0 by 1 or whether it will decrease Betti minus 1 by 1. Okay, so let's try to verify this, right? So the first thing we notice that the dimension of this is 0, right? And in this incremental algorithm, what we saw was that whenever p is 0, the 0th Betti number will increase by 1, right? So okay, so I think I stated this incorrectly. Since it is p is 0, okay, we are directly going to increase Betti 0 by 1, right? We don't have to check any condition, because in this case one can show that the condition actually trivially holds. All right, so Betti 0 we'll just increment by 1, and so now what we have is in delta 1, right? Delta 1, I hope you agree, has only this vertex 1, and the answer is that the Betti numbers of this simplicial complex are Betti p is 0 for all p, but Betti 0 is 1, right? Now let's, so this is step 1. Okay, the first iteration is done. Now in the next iteration, delta 1 is having this vertex 1, and I'm going to add this vertex 2 to this, right? And again, I notice that the dimension of this face is 0. And since I'm adding, vertex to the existing simplicial complex, I have to simply increment Betti 0 by 1, right? So incrementing Betti 0 by 1 will tell us that the Betti number now becomes 2. Oh, what have I done? This is 2 over here. All right. Okay. So what I have is I started off with 1. Now I have added this vertex 2, and all I am claiming is that this vertex actually increases by 1. Okay. This Betti 0 actually increases by 1. Now let's look at step 3. So in step 3, I'm adding this vertex 3 to it, right? So I started off with this simplicial complex, and I'm adding this vertex to it, right? So since I'm adding this vertex to it, the Betti 0 will again increase by 1, and now it will become 3, right? So far so good. So in step 4, what I have is I have these 3 vertices. Okay, and I'm now going to add this edge over here, right? So this edge is what I'm going to add, right? So now let's verify the condition. So the verifying the condition is I have to first look at daba 1 of sigma 4. So daba 1 of sigma 4, this is the edge, so I will end up with 1 plus 2, right? And I have to ask what is daba 1 of delta 3. So notice that delta 3 has only these 3 vertices. It has no triangle, it has no edge, right? So if I apply daba 1, right, I hope you agree that the image of daba 1 of delta 3 is going to be trivial, right? So in that sense, 1 plus 2 does not belong to the image. So this condition is not satisfied in the sense that this does not belong to the image. That's why whenever I add this edge to it, this will lead to destruction, right? So when I'm adding this edge over here, right, the Betti 0 will reduce by 1. So you can see that now Betti 0 will become 3 minus 1, which is 2, right? And that is what we expect. In this simplicial complex, there are basically 2 components, and that's why Betti 0 is 2. Now let's see what happens when I add the edge to 3, right? So now I'm adding this edge over here, right? So this edge is now what I'm adding, and the current simplicial complex, maybe I'll use red color to denote my current simplicial complex, and maybe blue color to denote what I'm going to add now. So now I'm adding this 2, 3. Again, I have to check whether 2 plus 3, which is, so let's say this is sigma 5. So daba 1 of sigma 5 is 2 plus 3. Whether this belongs to image of daba 1 of delta 4, right? This is what I'm interested in knowing. Well, daba 1 of delta 4, this image will only include the trivial element and 1 plus 2, right? Because of this edge being present. So I will have 1 plus 2. So clearly this 2 plus 3 does not belong over here. So whenever I add this edge to this simplicial complex, again we will have destruction, and Betti 0 will now reduce by 1 to 1, right? And this is what we expect, because in this simplicial complex you can see that after I have added this edge, the Betti number will actually decrease by 1, and the answer would be 1 here. Is this okay? So this simplicial complex only has one component, and that's why getting Betti 0 equals 1 makes sense, right? And the last step is when I add this edge 1, 3 to this simplicial complex. Okay, so let's try and understand what is the scenario. So I have 1, 2, 3 over here, and I'm adding this edge 1, 3 to this situation. So now let's see what is DABA 1 of sigma 6. So I hope you agree that this is 1 plus 3, and image of DABA 1 of delta 5. I hope you agree this is 0 plus 1 plus 2, 2 plus 3, and also 1 plus 3. Right, so you can see that this 1 plus 3 comes because of 1, 2 plus 2, 3, and this lies in the image. So when I add this, this edge over here, this will now lead to creation, right? So Betti 1 earlier was 0, and now after I add this blue edge, the Betti 1 will actually increase by 1, and the final Betti number will be 1, right? So and at this point I stop, because I have added all the faces that were there, and I ended up with this simplicial complex, which is whose Betti number is what I was interested in computing, right? And the final tally of the Betti numbers will look something like this. Betti 0 is 1, Betti 1 is 1, and all other Betti numbers are 0, right? And you can see that indeed the final numbers that we end up with are the Betti numbers that correspond to this, in the sense that there is one component and one two-dimensional hole here. Okay, so now maybe I'll pause here for a couple of seconds. If you have any questions, please let me know. Do you have any questions on how we went about with this algorithm? Yes, Ankit.
Sir, it seems like the algorithm will only work when we provide it the correct order of faces. Is that correct?
Notice that correct. So correct order here means that at each step we should have a simplicial complex. That's all.
Yes. So is there a computational method to get that order?
So the simplest way will be to add order all the faces first. So you first order all the zero-dimensional faces, then you order all the one-dimensional faces, then you order all the two-dimensional faces, and so on. This will be the simplest thing to do. Do you agree?
Okay. Yes, sir.
Right.
Thank you.
Okay. Are there any more questions? Yes, Durjati, please go ahead.
Can we get the homology groups from these numbers? Is there any way?
So homology, I'm not sure what do you mean. So your question is, can we get the the homology spaces, right? So you're asking, can I? So let's say this is the final simplicial complex delta. So your question is, if I know beta p, can I know HP of delta? Is that your question?
Yeah. Is there any way?
So is there any way, right? So this is equivalent to asking, if I give you a dimension of a vector space, can you tell me what the vector space was? Do you agree?
Yes.
So here I'm giving you the dimension of the vector space, and I'm asking you what can you say about the vector space itself. So I hope you agree that the question that you're asking is in that spirit. I'm telling you the dimension of a vector space, and you are sort of wanting to know what the elements of the vector space are. Okay, so of course elements of CP of delta is not that difficult to find, right? However, the hard thing is in finding ZP of delta, right, which is the set of P cycles. And then the hard thing is in finding this BP of delta, and then taking the quotient of ZP of delta with BP of delta, and then finding all the elements. Is this okay? So I am not aware of any efficient way, once you are given the dimension of a vector space, to figure out what this HP of delta is. But I can tell you that there are algorithms to find the generators of this HP of delta. Okay, so when I say generators, the way to interpret this is, I hope you agree that HP of delta, right, is a vector space and what should I say? The dimension beta p will equal in some sense the number of basis elements of HP, right? Number of basis or elements in the basis, number of elements in the basis of HP, right? So one would like to know, can you find some so let me maybe elaborate a bit. So let's say beta p is 2. So what does this mean, right? So this means that HP of delta must be of the form something like this, right? So and maybe there is a plus b and so on, right? So I hope you agree that if beta p is 2, then HP of delta should have 4 elements, right? So why am I saying 4 elements? Because I hope you agree that this is a vector space of dimension 2, right? So it should have 4 elements. But what is difficult is, can you identify a representative of this class and can you identify a representative of this class? Is this okay? Because a representative of this class will represent one of the cycles, and a representative of this class will represent one of the other cycles, right? So identifying these representatives, okay, so that is a research question in itself, and there have been several attempts to answer this question. Is this okay?
Yes, sir, understood.
Yeah, are there any more questions?
If the beta is 0, then we can say it is a trivial 0 space.
That is trivially true. There is nothing, that's obvious. Is that okay?
Yeah, okay.
Are there any more questions? All right. Okay. So in the rest 15 or so minutes that we have, what we will do is we will try to build a case for how the proposition should be proved, right? So by the way, I would like to emphasize that if you want to see a formal proof of the proposition, okay, there was a recent work of ours, okay, so this is Scaraba, Thoppe, and Yogeshwaran, okay. So this was published in 2020, right? So this paper of ours provides a proof of this proposition that I stated, on the second page, right? So we sort of say that this condition holds under a general condition on, not just working with these homology groups over Z2 vector spaces, but we can also work under these general vector spaces, and this condition actually holds. Okay, so if you want to look at a formal proof of the proposition, you can look over there in this work of ours. You can go to my scholar profile and you can look at this paper over there. All right, but what I'm going to do is I'm going to sort of give a quick intuition of how one can go about proving this proposition over here, right? So instead of trying to prove it in in significant generality, what I'm going to do is I'm going to look at a special case, right? And maybe prove it for that special case, and the same idea you can extend it to other situations as well. Okay. All right, so maybe this is a good example that we can discuss. Okay. All right. Okay, so so let me re-emphasize what we are trying to do. So our goal is to prove this proposition. So the proposition, if you recall, was something like this. Let's say you had some simplicial complex delta, to which you added this phase sigma, and sigma had the condition that sigma did not belong to delta. However, dabba p of sigma belonged to what should I say? Cp minus 1 of delta, right? So this condition says that the phase does not belong to delta, however all its boundary phases belong to delta, right? And three things can happen. First is that all other Betti numbers are preserved, right? So after you add sigma to it, right, after you add sigma to it, the Betti numbers are preserved for all j not in p minus 1 to p, right? And the other thing is if your dabba p of sigma lies in the image of dabba p of delta. If this condition is true, then beta p will actually increase by 1, right? So beta p will increase by 1. And on the other hand, if dabba p of sigma does not belong to image of dabba p of delta, then the p minus 1th Betti number will decrease by 1. Right? So this is the proof, this is the claim of the proposition, and we need to prove this. Now, instead of trying to prove it in too much generality, what I'll do is I'll look at this very specific example and show you how the proof goes about. On one hand, this will help you understand the the way the proof works, and you should be able to extend it to the general p case as well, right? So let's look at this example, and the idea is that we have to make use of the corollary that we had to the Mayer-Vittoris theorem. Okay, so corollary to Mayer-Vittoris theorem, that's all we have to use. All right, so let's see. So what is the situation, right? So this is the simplicial complex whose Betti number we are interested in knowing, right? And this is the simplicial complex that we begin with, right? So notice that the difference between this simplicial complex and this simplicial complex is just this face, right? So this triangle, once you add to K1, I hope you agree you get M, right? So I hope you see that the relation between M and K1 is that to K1 you add this triangle, and once you add this triangle you will end up with M. Is this okay? And our goal is to figure out, if I add this triangle to K1, how does the Betti number of M relate to the Betti number of K1? Okay, so that is the question that we are interested in knowing. Is this okay? So I hope you agree that M is K1 union sigma. Okay, K1 union sigma, and this sigma over here is this triangle 1, 2, 3. So I'm going to add this 1, 2, 3 to K1, and I'm interested in knowing what is the Betti number of M. Is this okay? So this is what I'm interested in knowing. Now, in order to apply this Mayer-Vittoris theorem, in particular the corollary of the Mayer-Vittoris theorem, notice that this way of writing K1 union sigma is not a good way, because sigma by itself is not a simplicial complex, right? So, to apply this Mayer-Vittoris theorem, we want that K1 and K2 both be simplicial complexes. So what we will do is, we will define K2 to be a collection of faces such that this forms a simplicial complex and includes sigma, right? So sigma over here is this triangle 1, 2, 3. So what I do is I take all the boundary faces of sigma, which is 1, 2, 3, then the edges 1, 2, 1, 3, 2, 3, and then I take sigma itself, okay, which is 1, 2, 3. So again, I would like to emphasize that when I write 1, 2, 3, I actually mean 1, 2, 3. Okay, so this is what I mean. Again, I don't want to write it this way and unnecessarily complicate this notation over here. But I hope it's clear that when I write K2, it's a collection of subsets, and this is a set with one element, this is a set with one element, and so on. And I have constructed this K2 in the minimal fashion, right? Minimal fashion meaning it has 1, 2, 3 and all the boundary faces of 1, 2, 3. Is this okay? And now I hope you agree that this thing that I had written before, I can now write it as M equals K1 union K2, right? So the difference between this and this is that here sigma is not a simplicial complex, whereas K2 is a simplicial complex. Is this okay? So now I am adding this sigma to K1, and that can be viewed as adding this K2 to K1. And now I will sort of relate the Betti number of M to the Betti numbers of K1, K2, and also to the Betti number of L, which is K1 intersection K2. Right. So in this discussion, we will focus on how the first Betti number of M relates to the first Betti number of K1, K2, and L. Is this okay? So that's what we are going to do. So let us try to understand that. So beta 1 of M, right? So from this Mayer-Vittoris theorem, right? I have already written it, so maybe I don't need to write it. So the first Betti number is related in the following way, right? So when M is K1 union K2 and L is K1 intersection K2, right? The first Betti number of M is related to the first Betti number of K1, K2, L in the following fashion, right? So you have Betti 1 of M equals Betti 1 of K1 plus Betti 1 of K2 minus Betti 1 of L plus dimension of kernel of new 1 plus dimension of kernel of new 0. Okay, so we will talk about this later on, but let's first try to evaluate what these different Betti numbers are, right? So first let's look over here, right? What is the Betti number? Okay, so you don't have to compute this over here. I will just tell you, and our goal is how does the first Betti number of M relate to the first Betti number of K1, right? So you can see that in this figure over here, there is a hole over here. That's why I hope you agree that beta 1 of K1 will be 1, right? On the other hand, your K2 is basically this simplicial complex. It has these 3 vertices and this 3 edges and this triangle, right? So there is no hole here. So I hope you agree that beta 1 of K2 is 0, right? So now let's look at the intersection of K1 and K2. So this is K1 over here. This is K2, right? So I hope you agree that K1 intersection K2 will be something like this. It will have these 3 boundary vertices. It will have these 3 edges, but there will be no triangle because this triangle and is not present over here. That's why the intersection of K1 and K2 will not include this triangle, whereas it will include these 3 vertices and these 3 edges, right? So this is how your L will look. And there is a cycle over, there is a hole here. That's why Betti 1 of L will be 1, right? So what we have known so far is beta 1 of M is 1 plus 0 minus 1 plus dimension of kernel of new 1 plus dimension of kernel of new 0. Okay, so this is what we have. Okay, so these things cancel off and I end up with beta 1 of M is kernel of new 1 plus kernel of new 0. Is this okay? So now in the remaining 10 5 to 7 minutes that I have, I will focus on computing this kernel of new 1 and kernel of new 0. Okay, so let's try to recall what these new 1s and new 0s are. So recall what new 1 is. New 1 is a combination of I1 star and J1 star. So what is I1 star and J1 star? Well, I1 star is the map which goes from H1 of L to H1 of K1, and J1 star is the map that goes from H1 of L to H1 of K2. And what are these stars over here? Well, these are the homomorphisms that are induced by I and J, right? So what is I1? So I is a map that goes from L to K1 and J is a map that goes from L to K2, right? So these weird arrows imply that I'm talking about inclusion operation. So the I1 of I1 goes from C1 of L to C1 of K1, and similarly J1 goes from C1 of L to C1 of K2, right? So these are your vector space homomorphisms, and if you recall, whenever we have a vector space homomorphism, in particular whenever we have a chain map, right, we have an induced homomorphism which goes between the homology spaces, right? So so we have to now figure out what is I1 star and what is J1 star. In particular, we have to figure out what is the kernel of new 1 and the kernel of new 0. So there is a typo here. I should write dimension of kernel of this plus dimension of kernel of this. Okay, so this is what I am interested in knowing. Okay, so let's try to figure out what these things are, right, and what is I1 star, J1 star, and in particular what is new 1, right? So let's first try to see what is L. Right, so L over here is this simplicial complex. Let me draw it again. So this is 1, 2, 3. Okay, so H1 of L, so this is L, will basically include all those representatives of the different cycles that are present over here, right? So as you can see, there is only one cycle over here, and hence H1 of L will include the trivial element, and it would include the equivalence class that corresponds to this cycle over here, right? So these are the two elements that are there in H1 of L, and it is easy to see that H1 of L has dimension 1 because of this basis element that I have over here, right? So this is something we have done before. That's why I'm sort of directly writing the answer, but this is something you will have to do it if I give you a new simplicial complex over here. Right, so this is H1 of L, right? Now let me write down what is what is this h1 of k1 and h1 of k2, right? So h1 of k2, okay, so that is easy to write. H1 of k2 is basically so what is k2, right? First let's write down what is k2, right? So k2 is made up of this simplicial complex. It has these three vertices, three edges, and this filled triangle. So clearly it has no cycle in here, right? So because of this reason, h1 of k2 will only include the trivial element, right? And now lastly, let's look at what is h1 of k1. So h1 of k1 is this. So this is 1, 2, 3, 4. Again, there is one cycle over here. Because of this reason, h1 of k1, okay, will also include the trivial element and the element that corresponds to 1, 2, 1, 3 and 2, 3. Is this okay? So this is what we have. And now let us try and understand what is this I1 star and J1 star. Okay, so that is what our interest is. Now we have to figure out what this I1 star and J1 star is. Okay, so what we will do is I1 star goes from H1 of L to H1 of K1, right? So I1 star goes from H1 of L to H1 of K1, right? So let's try to apply this I1 star on each of these elements. Just 1 minute. Yeah, so let's try to apply this I1 star on each of these elements that we have, right? So how is the I1 star defined? So I1 star on this equivalence class of 0 is you first apply I1 on 0 and look at the equivalence class, right? So let me emphasize that this equivalence class is in H1 of L, whereas this equivalence class is in H1 of K1. Okay, so this is the definition. So I1 of 0 is simply 0. So this I1 star maps this equivalence class 0 to the equivalence class 0. Now let's see what happens over here. It takes I1 star, it takes this equivalence class 1, 2, 1, 3, 2, 3, and you apply I1 to 1, 2 plus 1, 3 plus 2, 3. And since this is, going to leave it as it is, so I have 1, 2 plus 1, 3 plus 2, 3, and this is the equivalence class. Again, this equivalence class over here is an element of H1 of L, whereas this equivalence class over here is an element of H1 of K1, right? So the key thing to notice is that I1 star maps 0 to 0, whereas I1 star maps this 1, 2 plus 1, 3 plus 2, 3 to this equivalence class of 1, 2 plus 1, 1, 3 plus 2, 3. Now let's see what happens to J1 star. Okay, J1 star maps 0 to J1 of 0, which is 0 again. Now what about J1 star of 1, 2 plus 1, 3 plus 2, 3, right? So this is what we have to be careful about. So this is J1 of 1, 2 plus 1, 3 plus 2, 3, and then you look at the equivalence class. This is in H1 of K2. Okay, so J1 of 1, 2 plus 1, 3 plus 2, 3 is simply 1, 2 plus 1, 3 plus 2, 3, and this is the equivalence class. And I'm claiming that this equivalence class in H1 of K2 is the equivalence class of 0 itself. So why is that? So notice that because of the presence of triangle in K2, right, 1, 2 plus 1, 3 plus 2, 3 lies in the image of DABA 2, which is precisely B1, right? So since it lies in B1, I hope you agree that 1, 2 plus 1, 3 plus 2, 3 will be equivalent to 0, right? So in other words, the equivalence class of 1, 2 plus 1, 3 plus 2, 3 in H1 of K2 will equal the equivalence class of 0 again, right? So what is the conclusion? That J1 star maps 0 to 0 and J1 star maps 1, 2 plus 1, 3 plus 2, 3 to 0 again, right? So now we can look at new one. So new one, what does it do, right? So new one on 0 is I1 star of 0, comma J1 star of 0, right? And this is 0, comma 0. Now what about new one of 1, 2 plus 1, 3 plus 2, 3, right? So this is I1 star of 1, 2 plus 1, 3 plus 2, 3, comma J1 star of 1, 2 plus 1, 3 plus 2, 3, right? This is what it is. So I should put some round brackets over here. Okay, so this is what we will end up with. I1 star maps it to 1 2 plus 1 3 plus 2 3, whereas your J1 star maps it to 0. Is this okay? Now, if someone asked you what is kernel of new 1, right? What is kernel of new 1? We have to basically look at how many elements get mapped to 0, 0, right? Now, the only element that gets mapped to 0, 0 is this equivalence class. That's why kernel of new 1 will only include this. And from this, one can conclude that dimension of kernel of new 1 is actually 0, right? And in the same way, you can see that dimension of kernel of new 0 is 0. And from that, you can see that once you substitute over here, you can see that, beta 1 of m is actually 0. Is this okay? So let me stop over here and let me stop recording, and you can ask me questions if you have.